Welcome to today's explainer. We are going to be looking under the hood of some of the absolutely most powerful tools on the internet right now. We're talking about the invisible engines completely changing how we research and answer complex questions. Now, if you use AI tools regularly, you already know their power, right? But have you ever actually stopped to think about how they pull it off? So how do AI search engines actually know the right answer? It sounds like a really simple question, but man, it is a monumental technical achievement. I mean, we expect cold, hard facts now, not those jumbled, hallucinated messes that earlier models were kind of notorious for throwing at us. So what exactly is the secret sauce here that prevents the AI from just making things up? Section 1, AI Search Engines Explained. Okay, let's dive right into this. The answer lies in an architecture known as RAG. That stands for Retrieval-Augmented Generation. RAG is essentially the core technology, the foundational bridge connecting a standard search engine with modern AI comprehension. Instead of just relying on whatever random facts it memorized during its initial training, RAG actually combines active, real-time information retrieval with generative AI. It's literally like giving the AI an open book test instead of a closed book memory exam. A perfect real-world example of this in your daily life is a platform like Perplexity AI. When you type in a prompt there, it doesn't just take a wild guess. It actively fetches the absolute most recent, relevant data from vast knowledge bases all across the web. It understands those sources and then seamlessly formats all that fresh data into a really clean, comprehensive answer just for you. Section 2, the RAG indexing pipeline. We're zooming right into the engine room now. To really understand exactly how all this data is prepped before you ever even type a prompt, we need to look at what's called the offline assembly line. I want you to imagine a massive, highly efficient factory. All of the incredibly heavy lifting, the organizing, the sorting of basically the world's information happens completely offline, way before the search engine even opens its doors to you. Now, this offline indexing factory operates in 4 exact sequential steps: parsing, chunking, encoding, and storing. Every single piece of data the AI might eventually want to use has to pass through these 4 specific stations. Step 1 is parsing. Think of this as the step where the factory is essentially unboxing its raw materials. You know, the internet is just completely full of messy formats, right? We're talking PDFs, highly complex web pages, raw text files. Parsing simply extracts the raw, usable content right out of all that clunky formatting. Moving on to step 2, chunking. Look, you just can't feed a 500-page textbook into an AI's processing window all at once. It's kind of like trying to eat an entire giant pizza in one bite. It's just not going to work. So chunking actually splits that massive extracted content down into smaller, much more manageable pieces. It breaks those raw materials down into bite-sized parts that the AI can rapidly scan later on. Then we hit step 3, encoding. And wow, this is where the real AI translation magic happens. An embedding model takes those plain text chunks we just made and transforms them into dense numerical vectors, which are often called embeddings. It literally translates our human language into a wildly complex, multi-dimensional coordinate system, capturing the actual semantic meaning of the text entirely in numbers. It's absolutely fascinating. And finally, step 4, storing. We take all those newly minted embeddings and we save them in a highly specialized vector database. See, while standard databases search for exact keyword matches, a vector database is specifically designed to search through these mathematical meanings. And that makes the eventual retrieval lightning fast and just incredibly efficient. Section 3, the power of chunking. Let's put a magnifying glass on this specific part. If we look really closely at step 2, we can see exactly why chunking basically dictates the success of the entire system. When it's done right, chunking breaks huge texts into semantically coherent segments. It keeps complete thoughts together. This maintains the context of the information and avoids all that irrelevant noise, which allows the AI to pull perfectly sized nuggets of data without getting distracted by a bunch of fluff. And this brings us to what we call the Goldilocks principle of RAG systems. Choosing the exact right chunk size is a super delicate balancing act. If the chunks are too small, well, you get really specific detail, but you completely lose the broader context. But if they're too large, you drag in so much irrelevant text that it totally bogs the system down. Finding that optimal, just right chunk size is what maximizes both retrieval accuracy and computational efficiency. The stakes here are actually pretty high. As they say, ineffective chunking can lead to poor retrieval results and incoherent responses. Think about it. If this foundational step fails, the AI pulls the wrong data, it loses context, and ultimately feeds you, the user, a totally hallucinated, useless answer. Proper chunking is absolutely the bedrock of successful RAG performance. So we've seen how RAG bridges the gap between searching and generating, and how the seemingly simple act of chunking dictates the intelligence of the entire system. So I want to leave you with this. If chunking is the absolute foundation of AI search, how will we optimize the chunks of tomorrow? As our knowledge bases grow to encompass literally all of human history, these invisible background processes are only going to get more complex. Keep an eye on these foundational technologies, guys. They are actively rewriting how we access human knowledge. Thanks so much for joining me on this explainer.